Welcome to our deep dive into lazy learning, focusing on the nearest neighbor classification algorithm. Nearest neighbor classifiers are foundational in machine learning, offering an intuitive approach to classifying unlabeled examples. These classifiers work by assigning an unlabeled example the class of its most similar labeled examples. It's like comparing a new food to something you've already tasted. Despite its simplicity, nearest neighbor methods are powerful. They are used in computer vision for facial recognition, in recommendation systems for predicting preferences, and even in genetic data analysis. The K-nearest neighbors algorithm, or KNN, is the most common variation, and it's both simple and highly intuitive. KNN classifies objects based on the majority class among their, quote, nearest neighbors. The parameter K determines how many neighbors are considered, and this choice directly impacts the algorithm's performance and decision boundaries. Similarity in KNN is quantitatively measured using various distance functions. The distance metric is key to defining, quote, nearest. Euclidean distance, representing a straight line, is the most common. Manhattan distance, on the other hand, reflects grid-like paths, like navigating city blocks. For instance, the Euclidean distance between a tomato and a green bean, based on sweetness and crunchiness, can determine its classification. The choice between 1 NN or K equals 3 can change the final predicted class. The correct choice for Coates' quote is critical for model success. A poor choice can lead to poor generalization. A small K can lead to overfitting, resulting in complex boundaries that fit the training data too closely, while a large K risks oversimplification. A good starting point for K is often the square root of the number of training examples. From there, testing multiple values will reveal the best performer. Data preparation is an essential step, especially for KNN, due to its reliance on distance calculations. Feature scaling is essential, because features measured on larger scales will dominate the distance formula, skewing results. Min-max normalization and z-score standardization are common methods. For categorical data, we must convert categories into numerical formats, using methods like dummy coding or one-hot encoding, ensuring distances are meaningful. Nearest neighbor algorithms are known as lazy learners. But what does this laziness truly mean? Lazy learners don't build an abstract model during training. Instead, they simply store the entire training dataset as is, waiting for a new prediction. This approach makes training fast, but prediction is slower because the algorithm must compare each new instance to all stored examples to find the nearest neighbors. In conclusion, KNN is a simple yet effective lazy learning algorithm. It relies on distance metrics and the choice of K to postpone generalization until the prediction time, making data preparation crucial. Despite struggling with noisy or high-dimensional data, nearest neighbor methods remain powerful tools across diverse real-world applications.